is scheduling. And this is a sort of a topic that is very traditional in project management classes and has direct relevance to some of the scheduling challenges that are faced particularly by the project managers within this class. And I'm going to preface it by trying to link it back to the material we handled in the last class, estimation. So in the estimation context, we tried to take tasks and divide them up, decompose them, as we said, into pieces, so that we could arrive at an educated estimate, an informed understanding of how long they might take. And we had a lot of sort of points of suggestion for that, including the fact that we shouldn't try to arrive at a single number alone, but a range of numbers. And even with that range, we should take care that it's not too narrow. That it helps a lot when we're creating an estimate, particularly of a larger deliverable, that we divide it up into pieces, small subtasks. And all those things are very good principles. But there's still something missing when it goes from, when it comes to going from those sort of estimates into an estimate for an entire sprint, an entire deliverable. Maybe it's 3 weeks long. Maybe in some, as in some companies here in Saskatoon, it's 1 week long. In some more traditional firms, it might be 3 months long. If we try to go from, we try to list out the tasks for that deliverable and assign numbers to them for how long they might take, perhaps in a range way. What's the matter with sort of just totaling those up? Let's assume for simplicity it's just a single number per task, a single best estimate. What's the matter with totaling that up to get an estimate for how long the entire deliverable is going to take? What would be the matter with taking these estimates for each of the tasks to be delivered on and just this one is estimated to take, say, a day, this other one 2 days, this other one 1 day, and 5 days. What's the matter with just adding those up, 1, 2, 1, 5, and getting 8, and saying that's how long it's going to take? Yeah.
Because there might be certain ways that the tasks integrate or depend on each other.
Good. Yeah. And that's the key thing, really. As normal, Janelle's on top of it, and she emphasized the key word, to wit, dependencies. Now, I'd like to unpack that a little bit more. Suppose there's no dependencies between two tasks. Suppose they're more or less independent. So maybe it's in one case something that's going on the app side, adjusting the user interface for the app, and the other thing, it's a database change that has no direct impact on the app. It's on the server side. What's the implication for that if there's no dependencies between them? What? Yeah.
They can be done in parallel.
They can be done in parallel. So dependencies, whether it's tasks like that or at a level of data flow of data and programs, dependencies, ladies and gentlemen, are often one of the key constraints, often the key constraint on use of parallelism. Computationally, in our teams, understanding the dependencies is often key for understanding parallelism. So we're going to be today doing a whirlwind tour through some aspects of scheduling with a particular eye towards software projects to try to understand how we can take into account these dependencies in a principled way and come up with understanding of schedule for larger blocks. Okay, so estimation gives us a sense of task duration and effort, but not project length. If we just assume naively we could total up the times for tasks. We're ignoring the fact that some can be done in parallel, some must be done in serial. Certain ones can't start till other ones have finished. So scheduling is a process that allows for turning many task durations into an estimate for the project length. It turns out in many projects it's also of great interest because it helps us understand cash flow over time, or flow of human resources. So why undergo this sort of scheduling? Well, for several reasons. It lowers the chance that you'll be hammered by a delay if something screws up, and assists in recovering from that delay and resolving responsibilities for the delay if it happens. Okay, it helps us sort of recover if we've tripped up, and helps us tripping up. It turns out that there's certain components of a schedule that are more important than others. Certain tasks that are the ones that really have to be watched, and others that can be allowed to slide a little bit because they're not essential for delivering the entire thing on time. One of the insights that comes out of scheduling is that not all tasks are equal. Some of them matter more in terms of guaranteeing that the project comes in on time, or guaranteeing that the sprint comes in on time, and others of them can recede into the background a bit because they're not, as we say, on the critical path. Scheduling can also help us reason about large numbers of different details, which for larger projects can become issues, and can help us manage resources. Okay. So it turns out schedules are used at many different points within a project. And one of the most central roles that I'm going to advocate is identifying critical path. Trying to figure out what are the set of activities, the path of activities, the sequence of activities that are the critical ones, in the sense that if any of them are delayed, the whole deliverable is delayed. Okay? Mark my words, a critical path being a set of activities that if any one of them is delayed, it's going to delay the entire deliverable. Okay? It turns out that scheduling can also be really useful for communicating between parties, thinking through issues, reasoning about resource needs such as testing machines or people, etc. Scheduling is an activity that many projects undertake as a central activity, and generally it's a type of shared activity that many people should look at. It's not ubiquitous. There's many things which we end up not scheduling. Minor activities, coordination, for example, in software development, exactly who is doing what at any one time. There's enough uncertainty about how long tasks will take that, generally speaking, it's not regarded as effective to try to schedule out exactly who's doing what at a given time in software development. You kind of have a dynamic scheduling going on where, if you finish up one task, maybe you get assigned another on the fly rather than pre-scheduling it. But what you can schedule is broad sort of lines of work so that you can coordinate more effectively. Okay. So I want to talk, and I spend most of my time at sort of a quantitative level on the scheduling tasks. And I want to introduce two levels that are extraordinarily common of constructs that are used for scheduling. Okay? The first of them is something called bar charts or Gantt charts. Gantt charts are one of the most common things you will see in project management today. There are, at this time, probably literally millions of projects worldwide that are using Gantt charts. And it's a reflection of the fact that they are very effective in communication. They're very effective at giving us a high-level understanding of how a project is anticipated to be played out. And they go back almost a century to the First World War. They're great, particularly for representation of simpler schedules or overall representation of a very complex schedule. The key shortcoming of them is that there's no dependencies captured. Okay, they're effective as a reporting framework for how we're expecting things, but rather than as sort of a primary representation for reasoning about things. So it'll be something like this. So year 1, year 2, year 3, you'll have tasks down here on the left, and you'll have successive times over here on the right. And regardless of whether it's days or years, the granularity, the point is you have a bar associated with a given activity that indicates when you anticipate starting that activity and finishing that activity. How many people in this room have seen these sort of things at one point or another? Yeah, virtually everyone, because they're ubiquitous. They're around. And you know, often if you go to project managers' offices, you'll see something like this, but with dozens and dozens of these bars on it, and with many weeks or days sort of illustrated horizontally. Now, this can give you a sense at a glance about where you're at in a project, what's going on right now, what tasks are overlapped, how long it will be until you start a new task. But there is something key that it's missing, which is dependencies. It doesn't really tell you which of these things depends on another. Now, why is that an issue? Why is it an issue, say, does construction here depend on engineering and design? Why is that an issue?
Well, if there's a delay.
That's it. Yeah. So exactly. So Tushita was saying, if there's a delay in one, you'd like to know what's the implications. What are the ripple through effects of that? What does this end up pushing back logically, right? What things are logically linked to that, so that if something comes in late, if our work with and Hibernate takes longer to master, or there's a mess up in terms of getting this machine requisitioned from this new virtual machine set up by Greg or what have you, what does that end up impacting? What things are going to be delayed because of it? That isn't really communicated here. This is kind of, you're anticipating what you expect to happen, but not being able to ask much about counterfactuals. What if this happened? And really, that's the main loss of Gantt charts. Very easy to understand, but challenging in terms of understanding counterfactuals. If this happens, if that happens, and reasoning about how these things are linked. So, partly to address that, about 40 years later, a method came up, and it's called the critical path method, CPM method. There's variants of this method that go by many names: PERT scheduling, program or dependence graphs, etc. And it originated at DuPont Corporation, which is a major chemical manufacturer. And basically it consists of a representation of a project as a directed acyclic graph, a DAG. Right? And so we have an ordering that's normally imposed. We topologically sort it left to right. Okay, meaning the children of a given node go to the right of that node. So if a given node has to start before, if A has to start before B and C are put to the right of A. Okay, and it's not a tree; it's a DAG, directed acyclic graph. So it's acyclic. There's no cycles in it, but we can have points where it not only splits, but where it merges together, right? So we could have something along these lines. It's directed. You have arrows indicating, so here it might be A, B, C. B depends on A, so there's an arrow from A to B, for example. So it's directed. It's acyclic. There's no cycles in it, and it's a graph, right? So these sorts of graphs are used. They're topologically sorted in this sort of way, and they are used to reason about how long it will take for a given line of work to play out. Okay, and each of these nodes associated with this, each of these vertices in this graph, are associated with some information. The duration, what depends on them. And then we're going to run a scheduling algorithm, which you folks will be responsible for. You're going to learn about it today. It's a very simple O of N algorithm to give scheduling recommendations for each of these nodes, okay, on this directed acyclic graph. Okay, so, you know, something like a Gantt chart will give us a map over time here, activities here, whereas with CPM, we'll have an activity on node framework where each node will be an activity, or sometimes you'll see activity on arrow where each activity is in fact an arrow here, okay? Today we're going to be focusing on activity on node because they're more common these days. Okay, so the basic steps of this are to, number one, list out tasks. Okay, you're going to enumerate the tasks, or if you were subtasks associated with the project, you're going to list them out. Okay, each of those, I'll call them activities sometimes. You could call them task or activity. You list them out. Now, for each one, you're going to at least estimate duration. Okay? The duration of that activity. Pick your units, time units. Days.
You mean intervals?
Hours. Sorry?
The estimation in intervals, or?
So in this case, the algorithm I'm going to be showing you works with a single one.
Okay.
A single number. You can, in principle, do this with trying to incorporate range estimates. The algorithm would generalize to allow you to handle that, but for simplicity, I'm going to be talking about using it with single numbers. Okay, so this is a duration. Now, variants of this further specify dollars or resources for a given node. Okay. We're not going to be talking about those again for simplicity. Those would allow you to estimate, for example, the resource demand over time or the cash flow over time. So we're going to be dealing here with duration for simplicity, a single number. And thirdly, for each of those tasks or activities, you're further going to be specifying dependencies. What other tasks depend on it? So here, A is depended on by B and C. That is, B and C depend on A. In this case, we're confining our attention, again for simplicity, otherwise it's going to require several lectures, to a case where B cannot be started and C cannot be started until A is finished. In general, and I've taught versions of this before, where we deal with the case of start dependencies or finish and start dependencies, or start and finish, or finish. You can have all four. Here we're only going to confine our attention to the ones where the B and C can only start once A finishes. Okay. And then we're going to run a CPM scheduling algorithm, and that's going to basically give us, for each node, each task, 4 things. Mark my words, 4 things, and you're going to be required to know how to compute them. The earliest that task can be started, given everything that has to go on before it. The earliest it can be finished, given everything that has to go on before it. The latest it can start to not delay the whole project or the whole deliverable, and the latest it can finish to not delay the whole deliverable. Okay? So we call it early start, early finish, late start, late finish. Those are the 4 things that are going to be determined here. Okay? Okay. Now, earlier, Tushita had noted the primal sort of significance of dependencies. If 2 activities have no dependencies upon them that relate to one another, then in principle they can be done in parallel. Okay? Relationships between activities represent constraints, and those constraints can be of several types. Physical constraints, you need to use this tablet for testing this version of the app, so you're not able to test this other version of the same app, something like that. Or you have a testing machine, which is a testing database that can only hold one set of contents at a given time, or what have you. These could be resource or financial constraints. We only have so many developers around. Managerial constraints, regulatory constraints. These constraints with A depending on B can be informational, so you can't start B until you know the outcome of A. For example, A sets out a set of APIs that B needs to depend on when it's being created. So these constraints are of many, many sorts. Okay, and we're gonna a bit abstract over that. So we're going to, as I noted, use this activity on arrow diagram, and this is very widely. This is kind of the standard these days. Over the past 15 years, it's kind of evolved to be the standard. You'll also hear it referred to as precedence diagrams, and this method, CPM, is the precedence diagram method. So if you go online and use online project scheduling tools, you use Primavera Project Manager, use Microsoft Project, you'll be using this basic method. And again, we're only going to be dealing with a situation where we have finish to start constraints. One node has to finish before another can start. So we'll have something like this. So start, and you have to develop, a help system, and you have to do some development. Two developers are going to be working in parallel, and each of them has to do some testing, and then there's some integration between them and some testing associated with that, and testing that with some internationalization features and some further integration with the help system, etc. So we're going to have diagrams along those lines. I'm going to skip activity on arrow. I want to cut to the chase with the CPM algorithm. Okay, so the CPM algorithm is going to be at the heart of analyzing CPM diagrams and their implications. It takes as input certain things we've just talked about. List of tasks, and for each of those tasks, a duration and dependencies. What other tasks depend on this one in some ordered way? Okay. And the CPM algorithm is going to be a simple algorithm. O of n-ton, in fact, theta of n-ton, runs in time proportional to the number of nodes, and here's the number of nodes, which basically derives early and late, finish, and start times. So early start, early finish, late start, late finish times for the nodes. Okay? I want to emphasize again. Early start, early finish, the earliest that we can start and finish given the other tasks that you have to do first. By contrast, late start and late finish are the latest you can start without delaying the whole darn project, the whole sequence of activities. These are not, and I want to emphasize, this is not the latest you can start or finish while being kept busy with other activities. It's the latest you can start or finish without delaying the whole shebang, the whole sequence of tasks, the delivery of the entire thing. Okay. So early start, early finish, so the earliest we could possibly start a node, given everything that has to come before. Latest, late start and late finish, the latest we could start that node or finish that node, that task, without delaying the whole project. Okay? And we are going to illustrate this using this sort of notation. So we're going to have tasks, and these tasks are going to be shown as sort of circles with quadrants in them, okay? And the tasks will be numbered to indicate task number. And then down at the bottom slice, as it were, will be duration. And this duration could be in hours, days, minutes, what have you. And then on the left-hand side, we're going to have, and actually we'll use this diagram here with the 6 slices. On the upper left is the earliest start date. The upper right, earliest finish. Okay? So again, 3 here would indicate the earliest we could possibly start this, given everything that has to come before us, is 3, day 3. And the earliest we could finish it will be day 3.1, okay, given everything that's come before. Down on the lower side, abutting the duration, come the latest finish dates and the latest start dates, okay? So 6.5 would be the latest time we could finish this task without delaying the whole thing, the whole project, the whole deliverable, the whole sprint. And 6.4 is the earliest, is the latest we could start it without delaying the whole thing. Now, given that we're only dealing with finish to start dependencies, these are going to have particularly simple relationships to each other. So the early start and the early finish will differ from each other by the duration. Okay? So what that's saying is here that both early start and early finish differ from each other by the duration. So in other words, given the early start, we could just get the early finish by adding the duration to it. Meanwhile, the late start is just the latest finish minus the duration. Okay? So if we know the latest we can finish this task without delaying the whole project, we can arrive at the latest we can start it by just subtracting the duration. Okay, so these, ladies and gentlemen, are going to be what the CPM algorithm spits out for us. We're going to give it task information, durations, and dependencies, and it's going to give us early start, early finish, late start, late finish. Okay, turn the crank. It gives us those things. Okay, now, this algorithm consists of 2 distinct passes. Theta of n, but involves 2 distinct passes over the set of all nodes. Okay? So, first, we're going to perform a forward pass, which determines the early start and early finish. Okay? And the fundamental realization here is that if we consider a given task, a given node, the earliest it can start is the maximum of the times the things that precede it have finished. So let's suppose here we're considering node D, which depends on B and C. It can't start until B and C are finished, right? The earliest D could start, therefore, is the maximum of the time that B and C have finished. If C is delayed, we still can't start D until it's finished, okay? So note the maximum. Now, the overall project duration, the duration of the whole thing is to be defined as the maximum of the early finishes for all the nodes leading up to the last point. So that's the first pass. And coming out of that, we're going to get a time for the entire deliverable. And then we're going to perform a backward pass that's going to determine the late start and late finish. And the key difference here from the forward pass is that for this backwards pass, we're going to be computing the late start and late finish instead of the early start and early finish. That's one issue. The second issue is that in order to compute the late, we're actually going to compute the late finish first rather than the early start being what we're computing and computing up the finish from that. Here we're actually computing the late finish first and then deriving the late start from that. And specifically, how are we going to compute the late finish? It's going to be the minimum, ladies and gentlemen, the minimum of the late starts of the following activities. Okay? So, going again to our diagram on the board here, if we have B, and it is followed by D and E, okay? And we have a late start of E and a late start of D. The latest, each of them can start without delaying the whole darn project. The latest B can finish without delaying the project is the minimum of those. Because if it goes over more than that, these are not going to be able to start on time, because these depend on it. So here, again, I'll list those three things again. Pay attention. Three differences in backwards and forwards pass. Backwards pass differs in that it's computing the late start and finish rather than the early start and finish as a forwards pass. Difference one. Number two, it is computing, in contrast to the, so in the forward pass, we first arrive at the early start and compute the early finish from that by adding the duration to it. Here, we're first computing the late finish and deriving the late start from that by subtracting the duration. That's the second way in which they differ. The third way in which they differ, ladies and gentlemen, is that in the forward pass, the early start of a node is the maximum of the early finishes of all the preceding nodes, the nodes that have to go before it. It's the maximum, because it can't start until all the things before it have finished. It's maximum. In the backwards pass, ladies and gentlemen, in the backwards pass, we are not considering the preceding nodes, we're considering the successor nodes, the nodes that come after this, and we're taking the minimum in order to determine the late finish of a given time. We're taking the minimum of the late starts of the things that depend on it. Because if we go later than that for our late finish, we're going to be delaying those. So if the latest they could start, if we have latest starts for each of those, we need to live by the most binding of those, the one that's the tightest, the one that is the earliest. So we take the minimum of all those late starts to determine our late finish for that in the backwards pass. Okay? Three ways in which backwards and forwards differ from each other. Now, I want to develop the intuition. There shouldn't be sort of rote learning of this stuff. There's a common sense to it. And you know, during your final exam, when I ask you questions about this, you should be able to recall this example. I would argue you use this reasoning all the time without realizing it. This algorithm formalizes it. Okay, so suppose we fast forward to Saturday. It's 8 a.m. You're going to arrange to meet your team for a bug party. And you've just woken up. And the question is, it's 8 a.m. now, and you've got some tasks that you have to undertake before you can get in. And you're writing them about when you're going to be there. Okay? So you got to take a shower. You got to boil water for a porridge breakfast that you can only eat at home. And you're going to eat, and then you're going to walk to campus. So the question is, what's the earliest time you could meet them on campus? So it's 8 a.m. now. What are you thinking about as you're trying to assess this?
Which tasks can run in parallel?
Which tasks can run in parallel is a large part of it. Makes a big difference if you're eating a best breakfast burrito you can eat while you're walking versus if you have to eat it at home, right? That's a significant issue. So you're thinking about which can be done in parallel, and you're thinking about the chaining of them. What has to come after what, right? Okay, let's suppose that taking a shower and boiling water can be done in parallel. Okay? It's an electric water heater, okay? You don't need a flame on the stove. Okay, so how long would it take you before you can eat breakfast? 10 minutes. That's the maximum of the time for each of these, right? You're taking a shower and you're eating breakfast. It's a maximum. I'd note that that maximum is reflected right here. It's the maximum of the early finishes of the things that precede it. For eating breakfast, the two things that precede it are taking a shower and boiling water. And the earliest we could start that eating breakfast is reflective of the maximum of these two times, which is 10 minutes. Okay? Okay, so there you see the kind of the logic of this idea that the early start of eating breakfast, as soon as we could start eating breakfast, is the max of the earliest we can finish these two previous tasks. So 10 minutes. Okay, then you eat breakfast. That takes 15 minutes. So now we've gone from 10 minutes after waking up to 25 minutes after waking up. And then you walk to campus, right? 20 minutes later, 45 minutes. Okay, so that's an example of a forward pass. We're trying to figure out how soon we can get there. What's the earliest time, the early start for meeting your team? That's basically that forward pass that we're walking through. Okay, now let's go to the backwards pass. Okay, backwards pass, the thinking about this is slightly different, but again, it's common sense. Okay, so suppose you have a plane out of the Diefenbaker Airport at 12 noon. You need to know what time to get up so as to make the plane. Suppose you want to take a shower, boil water, eat breakfast, call and wait for the cab. You want to take a cab to the airport, you check in, sit at a gate for 20 minutes, and you sit on the plane. So you want to be at the gate or on the plane for a good hour before. For what time should you set the alarm? So here what you're doing is you're reasoning back, right? The plane leaves at 12. You're reasoning back from that. Okay, when do I have to get these activities? And, you know, here we're dealing with sequential activities, so it's pretty straightforward all the way back to eating breakfast, right? Well, and waiting for the cab. Maybe you can do that while eating breakfast, right? And so you're going to be reading back from this from 12. So, you know, I need to be basically at the gate an hour before 12, so 20 plus 40. So I need to be there at 11. I need to therefore check in by 10:50. I need to take therefore a cab to the airport by 10:30. And therefore I need to then start. Now these two activities might be done in parallel. I need to call the cab by 10:10, right? But meanwhile, I'm going to be able to eat breakfast during this time. And fundamentally, what one's doing in this case is you're deriving the late finish of an activity. You're subtracting off the duration to figure out when you have to start that activity. Okay? That's what we're doing, working back through there. And the key reasoning when it comes to parallel activities is you want to, when you're considering, you know, if I need to call a cab at 10:10, or I need to eat breakfast, you know, by 10:15, start eating breakfast, then I'm going to need to start boiling water by 10 minutes before the earlier of those. Excuse me, I've got to be careful because boiling water is with eat breakfast. But fundamentally, you're going to be dealing with which of those is earlier to go back. So here, ladies and gentlemen, we have a forwards pass and a backwards pass. The backwards pass works back from the end. The forward pass works forward. In one case, you're deriving early starts. The other case is you're deriving and then deriving early finishes from that. In the other case, you're deriving late finish and then deriving late start from that. Okay? And the tricky reasoning has to do with cases where you've got things in parallel. So we're going to go through a little example of this on the board, and we're going to work through this reasoning to make sure that we're on the same page. So basically, we're going to have a set of tasks and a set of durations, and they're going to be arranged in a form like this. So I'm going to draw this out, and this is using the same basic technique I noted earlier with these sort of these circles divided into pieces. Okay, so we're going to have a start here. And there's going to be a set of these nodes here, and I'll have to draw these in pretty close succession here. So this will be node 1, node 2, node 3, and then node 4 and node 7. Okay, and unfortunately this is going to pose a little bit of an issue. And then down here we're going to have node 5, and we're going to have node 6. Okay, that's inartfully done. Okay, and then we're going to have the end, which appears here behind the board. That'll be fine. Okay. So we're going to have these nodes. And recall that we're going to have early start up here in the upper left, early finish, late start, late finish in the lower left and lower right. Okay? Okay, now the durations are also shown here. 2 days, 7 days, 2, 2, 6, and then 4 and 4. Okay? So these are the dependencies. So what this is saying, for example, help contents can't be put together until the visual design of it is done. The localization can't be done to translate to multiple languages until the help contents are done, etc. And we're going to walk through the forward and backward algorithm. So what is the forward algorithm deducing here? What things do we get out of the forward algorithm? Yeah, the early start and early finish. Okay, now I further noted that really in this form of it, you only have to worry about deriving early start, because early finish is just early start plus what? Duration. That's not always the case. For precedence diagram method where you have start to start dependencies or start to finish or what have you, it actually gets rather more complex with that. But for this case, it's quite simple. So really we have to focus on the early start. So, ladies and gentlemen, we'll declare, without loss of generality, the early start to be 0 for the entire project. Okay? This is the start. So it's day 0, you could see, start. Okay. Okay, so given that, what's the early finish of activity 1? 2. Okay, good. What's the early start of activity 2? 2. It only depends on one thing. It's completely straightforward. And what's therefore the early finish? 9. The early start plus the duration. 9. Right? What's the early start of 2? 9. Okay, finish? 11. Early start of 4? 11. Okay, 13. And early start of 7? 13 and 19. Okay, good. So that is extraordinarily straightforward when you have a straight line path like okay? Where it's going to get more complex is if you have multiple things merging together, as you will over here, okay? Okay, we're going to come to that, but meanwhile, let's consider this, okay? So now for this downwards component, when's the earliest that 5 can start? 9. It depends on 2. I should make these all directed arrows to make this very explicit. So it depends on 2. And 2 doesn't finish until time 9 at the earliest. So the earliest it can possibly start is 9. And then it runs till when? If it starts at 9, when will it finish? 13, right? 9 plus 4. Okay, 6. When 0 it can start? 13, and the earliest it could finish? 17. Okay, good. Good. Okay, so, excuse me, 17? Yes, 4. Just reading this back, yes. Okay, so what is the earliest that the entire project can be finished? Okay, this is adverse, I hope I... When's the earliest it can finish, ladies and gentlemen? 19. 19, okay. So the earliest it could finish is 19. Now, what does this mean in terms of the latest that these two can in fact finish without delaying the whole project? What's the latest that number 7 can finish without delaying the whole project? Without delaying the finish time? Yeah, which, well, here, that is being dictated by the longest path here, so it's 19, okay? There are times we have it imposed from outside, but we're assuming here that we're interested in scheduling where the latest time for the deliverable is dictated by the activities to be done before. So it's 19. And when's the latest that this guy could finish in the lower, this sort of lower branch? When's the latest it could finish without delaying the whole thing? 19. So ladies and gentlemen, if it doesn't finish at 17, it's not a big deal. If it finishes at day 18, it's fine as well. Finishes at day 19, it's fine. It still hasn't delayed anything because this thing is still going on up here. Okay? Okay, now so let's walk these back. Day 19, that's the latest it can finish without delaying the whole package. So what's the latest it could start? 15. Okay? Given that that's the latest it could start, what's the latest this guy could finish? Node 5. 15. What's the latest it could start? 11. Good. We'll get further back in a minute. Okay, for this top sequence. So node 7, the latest it can finish is 19. If it's any later than that, it'll delay the whole project, the whole deliverable. So what's the latest it can start without delaying things? 13. Okay, node 4, what's the latest it could finish? 13, latest it could start? 11. Okay, node 3, latest it could finish? 11, latest it could start? 9. Good. You'll notice something here about all of these guys. What's different from those from the ones below in terms of the relationship of the late start and finish on the one hand to the early start and finish on the other? Yeah, their paywire is the same, right? The late start is the same as the early start. Late finish is the side of the early finish. Ladies and gentlemen, that's a sign that that is the critical path. We'd say that there's zero float, there's zero give, there's zero slack. You can use different terms to describe it. But basically, this upper path has to go on time to avoid delaying the entire project. By contrast, this lower one has slack. It has give. It has leeway. It has float. It has 2 days of float. We could actually start node 5 at day 11 and not delay the entire project instead of starting at day 9. There's 2 days to float here. In short, the earliest start for a node is different, off by 2 days, from the earliest finish. Sorry, from the late start. Okay, but now let's finish our derivation here. So, ladies and gentlemen, we have a branch here after node 2. So I'm asking you to reason about this. Okay, so we already know that the latest, or the early finish associated with node 2, the earliest it can finish, given everything that has to come before it, is day 9. When's the latest it can finish without delaying the whole project? 9. It has to finish by 9 in order to allow what to occur? To allow number 3 to start up. This one in the lower path, it doesn't have to start till what day? It doesn't really have to start till 11. But the point is, node 2 has to finish by 9 to 11, because it's the minimum of the things that depend on it. If there's one thing that depends on it that has to start earlier than the others, it has to finish in time for that, or else it will delay the whole project. So this 9 here in node 2 is reflective of the fact that if we finish any later than that, it's going to lead to a ripple through effect that's going to delay the entire thing. We won't be able to finish in time for us to start up later nodes in a way that would allow for finishing the project on time, the deliverable. Do you see that? See that point? Okay. So having done that, what's the earliest it can, or the latest it can finish, or it can start without delaying the whole project? 2. Good. And this guy, node 1, the latest it can finish, or without delaying the whole project? 2, and the latest it can start without delaying the whole project? 0. Good. Okay, so ladies and gentlemen, we've just done a sample two-pass algorithm. In the forward pass, we calculated early start, early finish. The later pass, the backwards pass, we calculated late finish and used that to derive late start. For the early start, as in this end node here, we basically took the maximum of the early finishes of all the things that preceded it. 19 is the maximum of 19 and 17. It can't finish the whole project until all the things that preceded it are done. And so it is with any node where we have things coming together. Okay. By contrast, coming back the other way, what we were doing is, and it occurred in node 2. We were determining the late finish and using that to derive the late start, and the late finish was determined by the minimum of the late starts of all the things that follow it. Because you can't finish any later than that without delaying the whole project, because one of those final ones won't be able to start in time to avoid delaying the whole project. So this 9 was the minimum of 9 and 11. Okay? Okay, so that's a two-phase algorithm. Now, clearly O of n time, we're just working through each node, way up, way back. It's straightforward, node by node. We just follow the dependencies. Now, we also noted, though, that there's a critical path here. The critical path here runs clear from start to finish. That's the nature of critical paths with these sort of constraints, where we have just finish to start dependencies. The critical path runs as follows. That's the critical path there. I'll make it more obvious. It runs like this. That is the path which is frankly most important. It's most important because if we slip up on any one of these nodes, if any one of them is delayed, if the duration is just a bit longer than expected, it will delay the entire project. We have no slack on these. We have no give. We have no float. As indicated by the fact that early start is the same as late start. Early finish is the same as late finish. That is the critical path. If we mess up in delivery of one, it's going to delay things. This lower path, we have a lot more latitude with it. We can delay things by a day, even by 2, without causing active problems. So the critical path here is marked by 0 float, as we say, 0 slack. We can compute the slack as either here, as either late start minus early start, or we can compute it as late finish minus early finish. Either one of those will give you what's called the slack, and that indicates basically how much leeway you have. Pretty straightforward idea. Powerful implications when it comes to complex nodes. Okay, so float and slack basically measure leeway in scheduling, give you a sense of the degrees of freedom in terms of performing tasks. And it's kind of the difference in when we have to finish things and the earliest the activity can be done. Okay? And it can really help you understand the bottleneck for the path for this deliverable. You know, at a practical level, keeping track of the critical path is really important. Critical path is the thing you have to get started on very, very early and watch very tightly, whereas other things you can be a bit more relaxed about. Okay? So one of the most important things coming out of the scheduling is this critical path. It's the longest 0 float path. For the algorithm described as at least one event, it determines the minimum time for the project. After all, the whole project finished at time 19 because this late finish was time 19. And it can evolve. Under what conditions would the critical path shift to this lower one? Give me a situation where it might shift to this lower path. If what happened?
A delay in the bottom one?
Yeah, a delay in the bottom one. So if let's say this first one here, instead of taking 4 days, it took 7 days. Suddenly, the critical path would be shifted from the top to the bottom, because now it's expected that that will be the constraint, right? So it would if it took 7 days, it would start, say, at day 11. Start at day 9, and could end up finishing then at day 16. This next one would start at day 16, would finish at day 20. It will have delayed the entire project. And now the bottom one is the critical path. It can happen. And the critical path therefore can evolve as durations take longer than expected. And often with the critical path, you'll want to watch it extremely closely. Sometimes you might even put contingency buffering in place, so you build in an extra few days on the critical path just in case, and have the project duration reflect that. Okay. Now there's generalizations to this algorithm that support multiple relationships between finish start, where you have to finish a node before starting the later nodes. They allow, as I said, start to start, finish to finish, etc. Okay. I noted that float is defined as late minus early, like the latest start minus the early start. That's actually called total float. There's a different variant called free float. Free float is basically the max time you can delay a node without delaying any of the successors. Not without delaying the whole project. It doesn't delay any of the successors. And this can be different. I give an example at the end of it I won't have time to cover. but where it is different. If there's a later node which comes in, it may be that free float is different from the total float. Okay. So if there's another dependency that comes in, for example, if you had something like this, or something like this guy here, you might get in a situation where basically without delaying the whole project, I can delay this by 6 days, but without delaying the next node down, I can delay it by up to 3. And part of the issue is, and this gets very contentious, there are huge lawsuits that take place over float. It's somewhat seen as a somewhat transgressive thing. It's if you stole my float, because you've shifted me into the position where I'm to be blamed if I delay at all. Whereas previously I had float, which gave me slack, which meant if I was a bit late, it would hurt things. So there's free float, and then there's a further notion called independent float. Just please note that there's that total float is not the only one. There is this notion of free float where we basically it's how much can we delay this, not without delaying the whole project, the delivery of the whole project, the whole deliverable, but instead it's how much can we delay it without delaying any of our downstream nodes. And I give some examples of a graph where you can reason about this. Okay. Good. I think we're over time now. I will look forward to being back in this room at 4 o'clock to hear your presentations. Are any stakeholders expected for today? Anyone? No? Okay. Good. Thanks.